Okay, in this video here, we're going to find a power series for the natural log of 1 minus x squared, and then we'll look at two other real short examples. So here we're given that the natural log of 1 minus x squared is equal to the natural log of 1 minus x plus the natural log of 1 plus x. That's using the product rule for logarithms, not product rule for derivatives. And that is going to be equal to the integral of negative 1 over 1 minus x dx plus the integral of 1 over 1 plus x dx. We're going to find a power series centered at 0, and then we're going to also find the interval of convergence. And so what we'll do is we'll go ahead and look at this. So this is the integral of negative 1 over 1 minus x dx. And if we have a over 1 minus r, that's going to be equal to the sum n equals 0 to infinity of a r to the n, provided that the absolute value of our common ratio is going to be less than 1. So we're going to go ahead and use that. And so you can see that the a is going to be minus 1, and your common ratio there is going to be negative 1. So I'm sorry, your common ratio is x, and your a is negative 1. Okay. So we'll go ahead and do that. And then before we integrate, we'll go ahead and write down some terms. So negative 1 minus x squared minus x cubed minus etc. minus x to the n, and then minus, and it continues indefinitely, dx for our series. Then we'll go ahead and integrate. So then we'll get a constant of integration, minus x squared over 2 minus x cubed over 3 minus x to the fourth over 4 minus etc. minus x to the n plus 1 over n plus 1. So that's our generic term, so we might want to use that when we're writing our series here, minus etc. So then that'll be c minus the series, and so we got x to the first over 1. So if we do start it at 0, we'd have x to the n plus 1 over n plus 1, and that's going to fit our pattern pretty good there. So we got our pattern for the first part. We'll go ahead and get the pattern for the second part, so we'll do the same thing. So for this one, we'll write this as 1 over 1 minus negative x. So your a will be 1, and your r will be negative x. Okay. So that'll be sum n equals 0 to infinity negative x to the n dx, and so we'll write out some terms. So 1 minus x plus x squared minus x cubed plus dot 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 negative x to the n plus etc. dx. So when we integrate that, we get a constant of integration plus x minus x squared over 2 minus plus x cubed over 3 minus x to the fourth over 4 plus etc. Negative 1 to the n, x to the n plus 1 over n plus 1 plus etc. And so that'll be c plus, and so if we want to try to start with the n plus 1 term, then we'd want to start our series at 0. So start at 0 to infinity, and so we want the first term to be positive, so negative 1 to the n will be sufficient, x to the n plus 1 over n plus 1. And so now we're going to go ahead and add these and see what happens. So both of these, your common ratio is x, and so x needs to be less than 1. So your interval of convergence will be minus 1 to 1, and let's go ahead and see what we got going on here, and that is centered at 0. So we're going to write out those two series. So there's the first one. Maybe we'll speed it up a little bit. Here we go. I'm going to try to. It's not letting me speed it up. Okay, well, we'll just let it go at regular speed. Now it's being really stubborn. Okay, there we go. Alright, so there's the first series. And then we'll write the second series. And it looks like the odd powers are going to absorb when we do this. So the odd powers of x are going to absorb. So we'll have a new constant of integration. We can call it c. So the x's will absorb, and then we'll have 2x squareds over 2. The x cubes will absorb, and we'll have minus 2x to the fourth over 4. Okay, and then the next one will be 2x to the 6th over 6 minus 2x to the 8th over 8 minus, etc. And so we're trying to come up with a pattern here. Looks like we're going by, looks like my pen's not being recognized. It is not. Hang on a second. Okay, so it seems to get the pen resolved there. All right, so even powers here, or even multiples here, and then the powers are even also, so we can see if we can come up with a generic way of describing that. So the generic term, they all have a 2, and then we have x, and we'll say 2n, and then divided by a 2n also. And we'll see if that works. We might have to make an adjustment there. And so if we do want to start it at 0, which I probably would like to have my series start at 0, then I would need a plus 2 to make sure that we start at 2 and then progress that way. Okay? And then the denominators are the same as those exponents. We'll do the same thing there. And then, of course, minus, etc. And so we can reduce a little bit so that becomes x to the 2. Oh, so I'm reducing here, sorry. So c minus x squared minus x to the 4th over 2 minus x to the 6th over 3 minus x to the 8th over 4 minus, etc. So it looks like I ended up doing that a little bit later, so we don't want to make that look like an equal sign. Okay, so minus x to the 2n plus 2, and then we reduce, that'll be n plus 1, and etc. So c minus sum n equals 0 to infinity, and we have our generic term x to the 2n plus 2 over n plus 1, and you can go ahead and check it. So if we plug in 0, we'll get x squared over 1, that's good. Plug in 1, we'll get x to the 4th over 2, so that seems to do what we want it to do. And our interval of convergence here is going to be minus 1 to 1. If you want, you can check the endpoints there. Okay. All right. The other... Oh, we got to do one more thing here before we move on. So here we're going to find what that constant of integration is. And so we'll pick a value for x. And so probably a good value to pick for x is to pick 0. So we'll put x is equal to 0. And so we'll have the natural log of 1 minus 0 squared, which is the natural log of 1, is going to be equal to c. And the natural log of 1 is 0, so that means c is equal to 0. And so the natural log of 1 minus x squared is equal to the series part. So the sum, a negative sum, n equals 0 to infinity, x to the 2n plus 2 over n plus 1. Okay, and that is our series. The last two examples, they're going to give us a series formula, and they're going to ask us to use that to evaluate, I think, a natural log and maybe the arctan. So let's say that we are given the natural log of x plus 1 is equal to the sum n equals 0 to infinity of negative 1 to the n, x to the n plus 1, I'm having trouble with my pen here again, divided by n plus 1, and using that very fact, find the sum n equals 1 to infinity of negative 1 to the n plus 1 over 3 to the n and then n. So if we're going to use this formula, the first thing we need to do is we need to roll back the index to 0. So if we roll back that index to 0, we're going to need to compensate, and to compensate we would need to add 1 to each one of my n's here to compensate for that. Now you would get an n plus 2 here, and so n plus 2 would be the same as n there, so we can leave it as an n. Okay. Alright, so let's go ahead and do that. So we're going to roll it back to index of starting at 0, and that'll be negative 1 to the n. And then what we'll do is that 3 to the n, that's going to act like our x to the n plus 1. So we can, and that 3 to the n is the denominator, so we can write it as 1/3 to the n plus 1, and then all over n plus 1. And that's going to be our x, which is 1/3. And so this is going to be the natural log of 1/3 plus 1, which is a natural log of 4/3. Okay, we're going to do one more of these. It's going to be a very, very similar construction where we're going to have to roll back the, my goodness, this pen. We're going to have to roll back the index here one unit there. Okay, so let's go ahead and move on to that one. So here we're going to be given the arctan formula, which is going to be, let's see what we have here. So the arctan of x is going to be the sum from 0 to infinity of -1 to the n x to the 2n plus 1 over 2n plus 1. And what they would like to do is they would like us to use that formula to find the sum n equals 1 to infinity of -1 to the n plus 1, 3 to the 2n minus 1, and then 2n minus 1. So if we're going to try to get it to fit this formula, we're going to roll that the index back 1, so then we'll have to compensate. So you're going to add 1 to wherever you see an n, so you have a 2n plus 1 in both the exponent, or you have a 2n minus 1 in both the exponent here and here, and so that you'll have a n plus 1 in place of the n, and then subtract 1, and so that's going to give us a 2n plus 1, which seems like this is rigged pretty nicely, so that's going to fit that right there. Okay, the x is going to be a 1/3 again like it was in the previous one, and when we add 1 to the exponent here on the alternator, it'll be the same as if it was just n here. Okay, so this will be the sum n equals 0 to infinity of -1 to the n, x to the 2n plus 1 minus 1, and then 2 n plus 1 minus 1, so that's compensating for rolling the index back 1. Okay, so that's going to be sum n equals 0 to infinity of -1 to the n, and then we'll rewrite that as 1/3 to the 2n plus 1 all over 2n plus 1, and so that's going to be, so here we're saying x is equal to 1/3, and so this is going to become the arctan of 1/3 there. Okay, so that is it for this video. We'll see you next time.